which is the last talk of the workshop. Costas will talk about Hopf twist and marginal deformations.
All right, so let me start by maybe clearing up some confusion. I think I'm listed somehow among the organizers, but I must say that my only contribution to organizing this was helping to transport the wine.
That's important.
Yeah, but I think I'm still qualified to thank the organizers for inviting me to talk here. So especially Mr. and Shinji did a great job in getting this thing running and getting us all here in this beautiful place. Okay, so I'll talk about some work that we did a couple of years ago with my then master student, Hector Glamini, who is now my PhD student, and some ongoing work with Hector and some other people, which I'll list later. But before that, okay, let me just in case people are not totally comfortable with the geography of South Africa, so Pretoria is here, just next to Johannesburg. It's, as I was saying, it's full of jacaranda trees which bloom purple in the spring, so every October or so. It's a very beautiful show. And this is just a view of the campus. It's a very pleasant and green campus, full of aloes, as I was just saying. Okay, so let's today I'll discuss some aspects of symmetries and integrability of the exactly marginal deformations of n equals 4, and explain why I think it's a useful perspective to take to generalize the notions that we use for symmetry of these gauge theories from Lie-algebraic to Hopf algebraic notions. The way I'll discuss these algebras, these Hopf algebras, is through something called a twist, which explains hopefully the title. Now the title is, I'm kind of abusing the terminology a little bit. Many of you must have heard of something known as a Drinfeld twist, and that's exactly what these Hopf twists I'm talking about are. I'm just using Hopf in a contradistinction to Quasi-Hopf, which I'm going to use at some point in the talk. Okay, so the idea is that after discussing these algebras, these Hopf algebras that I'm interested in, and a specific star product that I use to sort of parameterize these, or to deform the Lie algebras into Hopf algebras, then I'll discuss for a specific deformation how you can use a generalized geometry description of type 2b in order to construct the dual supergravity background of these exactly marginal deformations. Okay, so very quickly I'll go through some introduction about n equals 4, although of course I don't think in this audience you need to say much. It's the n equals 4 super-Union theory is a unique four-dimensional gauge theory with maximum local supersymmetry, and it has many beautiful properties, perturbative finiteness, as was derived in the very early 80s, I guess. Then non-perturbative finite, I think also one should mention probably contribution of Mandelstam as well in some of these early works. It's known to be non-perturbatively finite. It takes part in the ADCFT correspondence, of course, as famously first introduced by Joe and Costas. It has planar integrability, so there's integrability in its planar in the sector of gauge invariant operators in the planar limits, and you can find the spectrum and all that. So there has been a lot of work since the early 2000s on this, and also its planar amplitudes also have very interesting structures. So the question is this the unique theory of these features? Or if it's not, which probably it's not, are there other theories which only share some of these features? And can we use this knowledge, all these many papers that, of course, I'm not citing any of them, have developed this formalism of integrability in particular to understand more realistic theory? So what we're going to do in this talk is look for theories which are as close as possible to n equals 4 without being n equals 4, and the natural place to start is these marginal deformations. I'm going to focus on n equals 1 supersymmetric theories, so these are just superpotential deformations and not affecting the Kähler part of the potential, of the Lagrangian. So in n equals 1 superspace, this is how you write such a theory. This is of course the kinetic terms and some interaction terms, but I only care about these superpotential terms, which are written in terms of chiral superfields, and the n equals 4 superpotential, that if you want to get the n equals 4 theory, what you have to plug in is something like this, in terms of the three scalars, three complex chiral superfields of n equals 4. This can be written also like this, and I'll come back to this in a minute. So now if you want to marginally deform this, classically, well, what you would like to do is write something like this. Of course, it has to be cubic in order to give you quartic terms in the potential, which are what you need for marginal deformations. And this Hij should be asymmetric just because this is anti-symmetric. Of course, this will be more general than purely symmetric, but you can show that with Fielder definitions you can get rid of many of those other components. And so basically, the most general thing you could do is have a symmetric tensor. But of course, there's many symmetric tensors that you can write. And so the question is, which of these deformations are exactly marginal? Out of those classically marginal ones. And there have been some perturbative approaches, but the main work I'm following is the non-perturbative proof of which are the exactly marginal deformations by Leigh-Strassler in '95, which kind of gave their name to these marginally deformed theories. And what they found, by looking at the LSBZ beta function and using, very crucially, a Z3 symmetry that guarantees that all the anomalous dimensions of the three scalars are equal, and so you can put them to 0 at the same time, and at the same time also make sure the beta function is 0. Then they found that the only real possibilities are these ones, where you deform the commutator to a Q commutator like this, and you also add this cubic, well, everything is cubic, but sometimes it's also called a cubic term, which has this extra parameter h, and you can easily see that if you put h to 0, q to be 1, then you recover the n equals 4. Of course, now you have this space of couplings. So kappa is also a new coupling, but you also have the gauge coupling, which is not written here, it's part of the scalar part. So you have these four couplings, and it turns out that there has to be a relation between them, so there's some function of all of those, which is in general unknown. Okay, so basically what we're discussing is this type of modular space. So you have n equals 4 is parameterized by its holomorphic coupling tau. So that's already, there's already a modular space of n equals 4 theories, that's n equals 4 point. But at each point here, you should in principle be able to deform in a two-dimensional modular space with parameters of these parameters q and h, supposing that you solve that function for kappa. For that extra parameter.
Why is this choice of h and q done in this particular way and not in other?
You mean why don't I have other symmetric terms or other?
You start with 10 coefficients.
Yes.
Out of 10, you choose 2 which look quite random.
Yeah, they look quite random, but that was the work. Yeah.
Is it symmetric or?
Sure.
Is it because they are Z3 symmetric or?
They are not.
Yeah, they are. There's a Z3 symmetry here, which is, actually I'll discuss the Z3 symmetry. Actually, there are several Z3 symmetries which play an important role. I'll discuss them in the next slide. Well, all I can say is, that's the main essence of Leigh-Strassler's work. They analyzed.
Well, okay, they did it first, and so they had the option to choose inconvenient variables. But many years have passed, and now we should treat it more seriously.
But do you have a suggestion of what else? Because there's no other terms that you can put. It has to be, but that would not be exactly marginal. I think you can easily calculate that at one loop level you're going to get contributions to the anomalous dimensions.
There are some gauge imbalance conditions that you could apply, and this will keep them gauge imbalance.
But would you be able to make this to make all anomalous dimensions exactly 0 to all orders? To prove it to all orders? Because this was an older orders argument, of course.
By supersymmetry.
Okay, then we should discuss it. That could be very interesting. But as far as I know, you need that Z3 symmetry to make the Leigh-Strassler proof. Now, if there's a smarter proof by now, of course, I would love to hear it. Okay, but anyway, so assuming this, the question is, what is this function? We don't really know. You can write it, and people like Offer, I guess, and so on have looked at this some years ago. I'll give some references later. And so to one loop, you can see that one interesting feature is that also n, the rank of the gauge group, appears in this function. Okay. well, if you take the planar limit, something simplified, but it doesn't become trivial. A very interesting case is the case where Q is just a phase, e to the I beta, with beta being real, which I'll be calling the real beta deformation. And that has been the most studied. So how do they compare with n equals 4? Well, these Leigh-Strassler fields are supposed to be exactly superconformal invariant in 4 dimensions. Do we know they decifred dual? For n equals 4, yes. For Leigh-Strassler, we know it for complex beta by the work of Luna and Mandelstam. So what they did is they did it first for real beta by doing something that you're probably all familiar with, the TST transformations, which I'll explain in a second. But then using the SL2R duality of supergravity, they would manage to complexify the parameter beta. And now we think, with some restrictions, of course, beta cannot be too large, but we should know the dual for complex beta. Integrability, planar integrability seems to only work for real beta.
But for Leigh-Strassler also the ABC dual, right?
Sorry?
For Leigh-Strassler, we don't know the ABC dual?
For Leigh-Strassler in general?
In general?
No, we don't know.
No?
No.
Okay.
That's kind of the point of this talk, of leading towards that. There has been quite a lot of work in finding this dual. Before Mandelstam, I think.
It's n equals 1, right?
Sorry?
It's n equals
N equals
1. And what cohomogeneity 2 or cohomogeneity 3? Or, I mean, how many variables are the function in the bulk?
How many variables?
So this complex, during Mandelstam, it's a function of 2 variables.
Yes.
And the general Leigh-Strassler is also a function of 2
It
variables?
should not be, no, it's still.
Or 3 variables. No, because for example,
No,
Leigh-Strassler is 3 variables. So
I'll show a metric at the end,
okay.
and you'll see. And I think that metric is the generic kind of metric, but it's for a special case, and which is not a real case. It's not a really new case. It's actually related to the complex beta case in some way, but you'll see the generic form of how these things should look, I think. So anyway, we can try to understand what makes this real beta deformation so special, and the reason that, basically I'll qualify that later. I'll actually be talking about a theory which is not real beta, but which is integrable, but the reason is because it's actually unitary equivalent to real beta. So basically the only possibility is real beta. So let's look at the symmetries a bit more closely at the level of the classical Lagrangian. So as I said, okay, we have the superconformal group, so in n equals 4, that's the full symmetry here. I'll focus on the R-symmetry subgroup, so basically the SU4 part, but of this SU2 plus 4, but in n equals 1 superspace, the manifest symmetry can only be this. And actually I'll be focusing only on the SU3, because I'm not breaking n equals 1. You might have heard of other kind of deformations called gamma deformations, which also involve this U1 in the deformation, and that they are non-supersymmetric. But I'll only focus on the supersymmetric. So this is the superpotential again. Where this is the invariant tensor of SU3. So the reason we have SU3 invariance here is because if you do a U SU3 transformation, then you get in this superpotential, you get the determinant of U's, and that is invariant. So if you transform phi to U phi, then that's invariant. Okay, I'm saying that it's a trivial fact, but I want to sort of generalize that fact in a minute. So if you now do the generic Leigh-Strassler deformation, which is this one, you break this SU3 generically to a discrete subgroup. But you still preserve these symmetries, and these are the symmetries that are crucial for Lie and Strassler, which, okay, maybe one can think more deeply about these symmetries, but you have the symmetry of phi 1 to phi 2, phi 2, and phi 3, which is going to be the most important in this stuff, and there's also another symmetry like this, where omega is a root of unity. If you add also a third symmetry, which is within the U and R, which goes like this is the usual part of their symmetry, then this, according to work of Aharoni and friends in 2002, shows that this becomes just a non-abelian dihedral. Again, I'm not going to be focusing on this because I only care about I don't care about this V1. It's always there. Now, if you have real beta, then you see that this term goes away. Actually, even for complex beta, this term falls away, and then you only have this, and the symmetry group is enhanced. You can actually have U1s instead of just these Z3s. Okay, and that was crucial for Luna and Mandelstam in doing their TST transformation. You needed these U1s because you want a U1 to do a T-duality, then you want another U1 to shift, and then you need to T-dualize back along the original U1. Okay. But now if you have Z3s, we cannot do these T-dualities along the Z3s, so that's part of the reason that we cannot do this, we cannot find the supergravity dual. Okay, you don't have these extra U1s. From the generic case. Oops. So what we showed in work in 2008 with Teresa Monson, we claimed that actually this SU3 symmetry, if you go to the Leigh-Strassler deformation, is not broken. It's actually Q-deformed. So what we showed, with a lot of qualifications and things that we don't fully understand, but to some level we showed this, that if you deform that deformation I showed you before, remember I took phi to U phi, and that U was an element of the Lie algebra SU3. Here, actually here, we group in that case. Now here I'm taking phi to T phi, where T is a matrix, but it's a matrix where these elements are non-commutative. Okay, so these are not C functions anymore. They are operators which satisfy these specific commutation relations. I'll justify these in a second. So if these T's, the claim is that if these T's here, if you take that potential, the deformed potential, and you transform phi to T phi using these T's, then, and they satisfy these relations where you can see, for instance, you can plug in numbers here, this is hard to read, but for instance, you could have that T11 times T12 equals Q times T21, T11, T12, T11. So basically, they're not commuting. Then, this potential is actually dry. We showed this not to all orders, we showed it to cubic level because that's the level that we needed for this potential to show that actually what we wanted to show here is that there exists something called the quantum determinant, which is a C number, it commutes with, it's central, it commutes with everything else, so they can put it to 1, and that is what you need for invariance of this potential. It's the equivalent of the determinant being 1. Okay, I'll take a different approach here, because we find it more easy to be more useful. And those of you who are familiar with quantum algebras, you know that there are always two ways of constructing a quantum algebra, which are dual to each other. One goes through the universal developing algebra and quantizing that, and that's the approach I'm going to follow from now on. So this work was actually, this matrix approach was what we did back then. I'm not going to focus on the definitions very much. All I want to point out is that in the overall structure of quantum algebras, so remember that in an algebra, the most significant operation you can have is to take two elements, multiply them, and get a single element. Right? Now, you can also do the opposite. You can take a single element and, of the algebra and act on it to create two elements. And the operation that does this is called the coproduct. Okay, don't worry about these. This is just to show that okay, there is some structure here that is dual to the usual algebraic structure. So a Hopf algebra is something called a bialgebra, which has both a product and a coproduct. And these two things are compatible in some way that I'm not going to enter into the details. So a Lie algebra is a Hopf algebra, but it has a trivial coproduct. Okay, so the coproduct, if you take an element of the algebra X and you take its coproduct, it just becomes this. So it's X times 1 plus 1 times X. And this is what we use instinctively also in quantum mechanics when we have a state which is made up as a product state, and we want to act with, for instance, the spin. The spin has no idea how to act on two copies of the algebra, so basically two elements of the representation space. But what we're actually doing implicitly is using this coproduct, the trivial one, to spread it out so that it acts as the sum of this plus that. And this coproduct is, of course, commutative. So tau is the operation that exchanges the two copies of the algebra, so you can see that if you exchange the two elements here, you get the same thing, so that is commutative. If now this became non-commutative, so suppose I took this, and instead of a 1 here, I put a q, okay, some number, then that would of course not be commutative anymore, and now we would be in the realm of, if that were compatible with the product of everything, we would be in the realm of Hopf algebra. Okay, so that's one way to introduce them. And one way to construct them was shown by Fadevre, Speaking, and Tartajan, which is basically using something known as an R matrix, which is basically an object, you can think of it as a tensor with 4 indices, because it lives on two copies of the algebra. And if you define your T's, which I showed a few slides ago using these relations, then this is a construction of a Hopf algebra. But this R matrix should, for the construction to be fully consistent, satisfy the Yang-Baxter effect, which I write here in indices, in case this notation with spaces is not clear to everybody. You can also look at the index structure. So the reason that we need the Yang-Baxter equation when we apply this construction, and this is how we got essentially those commutation relations that I wrote down before. We just applied this. We know, I'll tell you how I got the R matrix. it guarantees that this algebra is not trivial. What this means is you're defining an algebra using quadratic relation. Now, how do you know that if you now look at the cubic product, you don't get any extra relations beyond those which come from the quadratic ones? Essentially, what you want to ask is, suppose I write a cubic product and I have some, I have some associativity, I impose associativity on my, on some relation built up of cubic or higher powers of my matrices. These things impose relations, and those relations might be extra, additional relations on top of the quadratic ones. The Yang-Baxter equation is what guarantees that this doesn't happen, that all the new relations from higher orders using associativity actually follow from the quadratic. In our case, we did not have the Yang-Baxter equation, which is why I was qualifying my statement that we found the Hopf algebra, because we imposed associativity, which could be a dangerous thing to do, because then that might imply that our higher relations trivialize the algebra, because if you have too many relations with the t's, then obviously at some point you have to start setting to 0. But what we showed is that at cubic level this does not happen, so we're consistent up to cubic level, at least. We have not looked at the higher level. Okay, how did I find this R matrix? This was really following our work of Roigman in 2003, who said that, okay, given a classical Lagrangian for some gauge theory and some matter in general, you can actually read off directly the one-loop spin chain Hamiltonian. So I haven't talked about spin chains, I'm not going to talk about spin chains in this talk, but this is the Hamiltonian that would act on gauge-invariant operators made up of 3 scalars. You can just read it off from the Lagrangian, and that's how it looks. And the R matrix is defined, and this was also partly done in work of Weisert and Roigman around the same time, that you define this is the Hamiltonian. Now, why is this is a 9x9 matrix? Because it's acting on the space. Remember, this is a nearest neighbor Hamiltonian, for those of you who know, have seen these things before. So this acts on a space of 2 copies of the scalar field. So when you see this, what this is acting on is on phi1, 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 phi2, phi1, phi3. So you make a basis like that, and that's why this is 9x9. So from that you can, with some permutations, you can define the R matrix, which is like this. So this is what participates in the Yang-Baxter equation. So so this R matrix here, you can plug it in the Yang-Baxter equation, and you will find that it does not, in general, satisfy the Yang-Baxter. Okay, so that's the problem that we have. You can check which case it does satisfy the Yang-Baxter equation. So how can I restrict my parameters Q and H, which are the only things appearing here, so that it actually satisfies the Yang-Baxter equations? If you do that, then you get the classification of the known integrable deformations of n equals 4. So the Yang-Baxter equation is crucial for integrability. Okay, we know that for many reasons, and this is another way of seeing that basically what you get is the beta deformation. So Q, you have to restrict Q to being just a phase, or you can get some theories which are equivalent to that case, and one of them I'll discuss in a minute, because we use it for something. But otherwise you don't get anything new. I mean, you can try to solve the Yang-Baxter equation, impose the Yang-Baxter equation. You get things that people knew already from studying the spin chain. So what we claimed, and I just said a minute ago, is that in the general case we still get the Hopf algebra. It's just not what is known as a quasi-triangular Hopf algebra, and you need this quasi-triangular condition, which we can take to mean the Yang-Baxter equation. So it's not exactly that, but it implies the Yang-Baxter equation. You can take that to be the hallmark of integrability, but in our case it's a Hopf algebra, but not a quasi-triangular. So we haven't analyzed this in detail, but in this talk I'll take something else. I'll do something else which we found easier to use and more applicable to what our eventual goal, which is to understand the supergravity side. So what we are going to claim, or what I have claimed, is that the global symmetry of the Leigh-Strassler theories is much larger than what naively sees by looking at the Lagrangian. Okay, so but to get this you have to expand your horizons and toolkit from the algebras to Hopf algebras. So the question is that I want to answer in this talk, so this is more or less introducing the theories and talking about work that was done some time ago. How do we work with such symmetries? And in particular, if I'm claiming that there is a quantum symmetry on the gauge theory side, so basically that I should be looking at this Hopf algebra, well, where is it on the gravity side? The gravity side, of course, has no quantum symmetry. It's not non-commutative. It's a very normal, smooth, deformation of S5 of the sphere. That's all you should need to do to get the dual. And if you can make this symmetry visible somehow, then you use it as a solution-generating technique to produce more of these deformed solutions.
So again, why do you call it quantum symmetry?
I'm using quantum symmetry in the context of quantum groups. So a Hopf algebra, I just want to avoid the word quantum group because it's kind of a misnomer.
But at the end of the day, just some stupid algebra. I mean, it's not, the word quantum, there's no H bar. There's no, I mean,
yeah, so whenever I say...
there's not the H bar of the n+1 and usage.
No.
No, okay.
No, all I mean is that, essentially the commutator, which was there in the n=4 square potential, now gets deformed to a Q commutator. So there's that parameter Q there, which I guess Q stands for quantum. But definitely it's not quantum in the physics sense. It's just a deformation. Think of deformation quantization. Yeah. So in that sense, it's quantum. The appropriate word to use would be Hopf algebras. If I just say Hopf algebras, then I know exactly what I mean. But just because, maybe quantum symmetry somehow might be more appealing than Hopf algebras.
Your comments about the quadratic relations and cubic relations, was that a comment about the algebra or about the physics application of the algebra?
Well, you see, in that paper, we wanted to prove it's a Hopf algebra, and Hopf algebras are associative. So we found those quadratic relations. So it's all about the algebra. It's not really about the physics understanding of it, although there is no... what I'm going to try to argue in this talk is that we should go beyond Hopf algebras into a structure which is non-associative. Okay, but back then, we were thinking, no, we have to have this Hopf algebra structure, so we imposed associativity by hand. We said, okay, let's look at all possible cubic relations between our T's, Tij's, which are the elements of our matrices, of our deformed SU3 matrices, and let's assume that let's impose that they're associative. That gave us relations, extra relations at cubic level, as it should, because we don't have the Yang-Baxter equation. We showed that these are okay, they don't kill the algebra, like we don't have to set any of these T's to 0, and actually they are enough to construct the quantum determinant, which is central and you can set to 1. So it's a pure element about the consistency of our construction. We were not thinking about the physics implications at that stage. We just said, okay, let's make sure we have a Hopf algebra, and that's what we showed. I'm going to move away from that paradigm now and argue that actually no, we should actually be looking at Quasi-Hopf algebra instead. I'm not sure if I'm fully answering your question, but... Okay, so as a first step to do this, let's focus on the integrable cases. And what I'm going to do is derive these integrable deformations of n=4 as twists of the n=4 structure, which I'll explain in a minute. Well, and what we'll be using is something known as a Drinfeld twist, which is, given, let's look at this formula here, given an R matrix, so if I give you an R matrix, which, say this 9×9 matrix, or it could be 4×4, depending on the situation, I can twist it by an F, which is an element of, again, 2 copies of the algebra. So you should think of it as something that has 4 indices, 2 indices for each copy, because it wants to rotate in each copy of the algebra. And you can do this rotation, this transformation, which looks a bit like a similarity transformation. But it's actually not a similarity transformation, otherwise we would be doing trivial stuff, and we would still be getting a Lie algebra. What this is doing, you can see the difference is that here I've exchanged the copies of the Lie algebra, of the algebra that I'm acting on. Okay, so if this was 1, 2, that would mean that it was just a trivial similarity transformation, but the non-trivial part comes because this is exchanged. The coproduct of the new algebra is actually related by a trivial similarity transformation, but the R matrix is related like this, and this is work of Drinfeld from around 1990. If this F satisfies this condition here, known as a co-cycle condition, which I'm not going to expand on very much, then this is going to give you a Hopf algebra. That's what Drinfeld showed. And for n=4, it turns out that this R matrix, which I had a few slides ago here, if you take n=4, so we're looking here, and you put Q to be a phase, Q to be 1, and H to be 0, then you just get the unit matrix. Okay, so what you can write as identity times identity. It's a 9×9 unit matrix, it's identity 3×3 times identity 3×3. So for n=4, this is trivial, It's just a unit matrix. So the idea is that now you can construct this full thing by twisting appropriately the n equals 4 R matrix, which is just unity. And I'll show some cases. So the beta deformation, you can take, this is the R matrix for the beta deformation. And obviously, as I said before, it satisfies the Baxter equation. But Bison and Rodman constructed this as a twist of n equals 4 case. And the twist, they did not write it explicitly, but you can get it from their paper. You can extract it. It looks like this. Okay, where this is, instead of q, you have q to the half in various places. And now if you can check that if you take a density matrix and multiply by f to 1 and f minus 1, then you get the correct R matrix. You can express this also in a simpler form like this, where h's are the elements of the Cartan algebra. Okay. So you're deforming essentially by the twist. This is called the twist f, and it depends on these elements of the Cartan algebra. Wedge here just means direct product minus the opposite direct product. Okay, so it's a wedge. But of course, this is a bit too simple. Everything is abelian, everything is diagonal. If we want to understand how to use these quantum symmetries, we would like something a bit more non-trivial. And that's what we did in the paper with Hector a couple of years ago. We looked at this theory, what we call the w-deformation, where you set q to be 1 plus w and h to be w is a real number. So this thing looks much more general than the beta deformation, because there's also the cubic part, because you see h is non-zero here. But actually it's unitary equivalent to real beta. So you don't expect any new physics, but you just expect things to be much more complicated because you're using the wrong basis. Okay? And that's what we wanted to do. We wanted to use the fact that this is equivalent to real beta, so we know its properties, and we have some control over it, but it also, the structure is much more, the features that arise are much more generic, and one can think of it as trying to do TST without actually doing TST. Because that's what we want to learn to do. How do we generalize this notion of TST to cases where you don't have the U1s? Here we have the U1s, but we're not using them. So we think it's somehow progress. And you can find the R matrix. It's more complicated than the beta deformation. You can write it in a more compact way in terms of some kind of shift matrices. It's not very important to go into the details. But what we found the twist. It's a bit more complicated. You can see there are non-diagonal terms in the twist. And this is actually a twist. It's abelian. I mean, that's no surprise because it's also related to the beta deformation. And from this you can, okay, there's also the inverse twist. It's not so important. What is important is that you can define a star product using this twist. So let me just quickly go through those ideas. So G is an element of my Hopf algebra. X and Y are elements of the module, the representation space that the Hopf algebra is acting on. So you should think of this as the symmetry. This is the spin, SU3, the global symmetry, acting on products of scalar fields, because these are in the fundamental representation of SU3. So the way Hopf algebra acts is like a derivation. So it should act, if you multiply two of these coordinates or fields, depending on how you think about them, then it should act like this. Now, if you deform the algebra, so instead of G, instead of the trivial coproduct, now you start using a deformed coproduct, which is what we're doing, you also need to deform the module product for things to be compatible. So you need to deform how you multiply your module elements, in other words, how you multiply your scalar field. So if I create a gauge invariant operator with my scalar fields, I need to deform that product between them in order to be compatible with my deformed algebra. And the way that works is that you need to define a new product here. What I called dot here, you could call M as for multiplication. And instead of the usual way that this multiplies them, you actually involve the twist. So in this case, the inverse twist. And that allows you to define a star product. Okay, so this is deformation quantization stuff. One can look at work of Kontsevich, for instance, this has been looked at in some detail. And so we have this star product, and you can also define something called the inverse star product, where instead of f minus 1 you put f. There's a reason for this funny language, but it's not so important. So in indices, all we're doing is we're multiplying these z's, which are just generically, I can call x and y, I can call them zi. I goes from 1 to 3, because these are our 3 scalars. I can multiply them with this twist. So what does that allow us to do? You can work it out. It's very explicit because we see if all the indices are there, we have the twist. So we can explicitly work it out. And what we find is that if I define the star product, I take the gauge theory trace, okay, which corresponds to the superpotential of n equals 4. This is just a commutator. If I want, I write it out and I put a star product between them. What it does, it gives me on the nose the superpotential of a w-deformed theory. And this you can generalize, because we have the full twist, so you can generalize it. Okay, so that's the idea we want to use. We want to see if we have the star product, how do we apply it on the supergravity side to actually twist correspondingly the appropriate structures of the geometry. Okay. Any questions about this? This is kind of one of the crucial formulas in the talk, that you can take the n equals 4 superpotential, put a star product. Of course, Mandelstam showed us how to do this for the beta deformation. We're generalizing, in this case, for the w deformation, but we actually know how to generalize more generally, or at least we're working on generalizing more generally to any deformation, even the non-integrable. And so this gives us the correct superpotential theory. You can also expand this to first order, this twist, and apply that star product. And what you get is a star product like this, which is much more similar to what has appeared in the physics literature, because it's expressed, so the non-commutativity is expressed in terms of a constant matrix, where, in appropriate basis, okay, in this case it's not constant, but there will be a basis where it is. And these matrices have been studied by Colaxisi about 11 years ago, where she found for the case of pure, well actually there are some details here, but these are for our case, but in her case she looked at the pure H deformation. So she put Q to 1, but H to be non-zero, so the cubic term. And she was trying to construct the supergravity background using the Seiberg-Witten method of mapping a non-commutative matrix like this to a B field. And she achieved it, but it only worked to second order in the expansion in terms of this Q, and in terms of this parameter H that she had. The reason it did not work further was non-associativity. So things start becoming ambiguous if you start doing this expansion order by order. But definitely we can reproduce her matrices. In this case, of course, it works to all orders because there's no issues with non-associativity. Okay. So let's go back. The new work that we're actually trying to finalize now, and should be out relatively soon, is that we now have the general twist. So you can write a twist that produces the full QH R matrix. Back then, 2 years ago, we only had the one for the W deformation. Now we have the full twist. You can see that it's a 9x9 twist. It depends on some complicated functions, A, B, C. I'll write them down on the next page. But it satisfies all the requirements of our twist, apart from the co-cycle condition, which was crucial for eventually for quasi-triangularity. So this is not going to be actually this is not going to be a Hopf algebra at all. I'll say what it is. So this is just if you want to see the details. I mean, this is how it looks. You can write everything in terms of 4 parameters, which here are called B, C, D, and F, and it looks kind of like this. And these are kind of messy, but they depend. They're 4 because there's 4 parameters: H, H bar, Q, and Q bar. These are complex numbers. So it just these seem to be a more appropriate basis than the original H's and H bars. It's still a mess, and we're trying to simplify these expressions to see if we can make some more sense out of it. So the claim is that this, and we've checked it to a large extent, this is not a Hopf algebra. It seems, the structure seems to be that of a Quasi-Hopf algebra, again introduced by Drilfeld, and discussed in the physics context, quite importantly by Black and Schomeris, who actually argued in a paper of '92 in general, like it is a kind of a general paper about what is the most general symmetry you can have in a physical or QFT context, and they claim that Quasi-Hopf algebras, even though they're not associative, they actually fit all the requirements, and one could in principle consider having these algebraic structures in QFT. There's nothing inconsistent. So these algebras are not associative, but the non-associativity is controlled by something known as the co-associator phi, which is an element now of 3 copies of the gates of the algebra. And so, okay, this might not make too much sense because it's in terms of the coproduct, but if it might make more sense to think of how the action is of the corresponding star product, how the action is on the module. So, of course, associativity would require that if you have something like this, that this should be equal to Z1, Z2, Z3. And this is a non-associative algebra, so this is not true. But what you can think of as happening is that you have to just put a phi here and a phi minus 1 here, which relate the two possible placements of parentheses. So a simple expression, if you put the parentheses on the second two, can become a complicated expression because this is a large linear combination of these things, because phi is a big tensor. Phi has 3 indices, 6 indices, I, J, K, L, and M. So you actually have full control of non-associativity. It can get complicated, but you know exactly what you're talking about. So if you have an expression like this, you can also write in terms of those, and vice versa. So that's the statement of Quasi-Hopf algebras. And you can generalize the Yang-Baxter equation to a Quasi-Hopf version, which I write here. There's a way to construct it, so we've done this. And we've shown that it satisfies this Quasi-Hopf Yang-Baxter, quantum Yang-Baxter. So we have a few more checks. There are some more identities, pentagon identities, and things we need to check, and we're busy doing that before we finally conclude it's a Quasi-Hopf algebra. Okay, that's all about the new stuff. So let's go back now to the gravity side. So far I've discussed, I'm going back to the associative setting now, and where we did this beta and W deformation. I showed you roughly how they look and how the star products look. How do we see it on the quantum, on the gravity side? So to understand this, I'm going to use the framework of generalized complex geometry, which I'm not going to say too much about, because I think it might get too heavy to start a totally new topic at this stage in the talk. But it's a framework which was developed originally by Hitchin and his student Bill Harry, and then developed by many physicists. I'm definitely missing many people here. And its goal is to unify complex and symplectic geometry, which on the physics side means that you're dealing with the metric and the B field on equal footing, which makes perfect sense for string theory. In string theory, there's the distinction between the metric and the B field is not really that big. To do this, you have to consider structure on the tangent plus the cotangent space of your manifold. And essentially now what we'll be focusing on is the space transverse to a stack of D3 branes, because that's what we use to construct a gauge theory. So I'm talking about n equals 4. So just think of having flat space, two-dimensional flat space. You put a stack of D3 branes, which cover the 4 dimensions, and then you have this transverse 6-dimensional space, which you can think of as C3. And in that case, so this is the space I'm looking at, and I'm going to be deforming that space. So I want to find what is the proper deformation of C3 in order to get these kind of structure that I was discussing. So you can think of a basis on this 6D space, this 12D space, which is these are the vectors. Okay, so these are the contractions, you can call them, the vector fields of C3. 1 bar, 2 bar, and then these are all the differential forms. Okay, I'm skipping the middle ones, but okay, so that's the basis. It's the tangent space plus cotangent space. You can define some objects here that satisfy Clifford algebra, and using those. So you can also define holomorphic and Kähler forms. Of course, the flat space. Okay, we know how they look. They look like this. Now, the new idea here, or the new thing that is possible by working on the tangent plus cotangent space, is that you can define objects called pure spinors, which, by the way, have nothing immediately to do with the pure spinors used for Ramond quantization, but they are pure in some way. But here, in this context, they're actually not even spinors, they are just forms. But what you can see here is this pure spinor is an exponential of the Kähler form. And if you expand it out, it becomes a multiform. So what we can do here, which normally you don't see in differential geometry, is that we add up forms of different ranks into one compact object, and we can consistently work with these kinds of objects. Now, people have analyzed what are the constraints on these pure spinors, in order to have an n equals 2 type 2D background. And it turns out that there are very few constraints. They have to be closed. These plus and minus. Here I wrote them for flat space, that's why there's a 0, but in general they need to be closed. And they need to satisfy some compatibility conditions in terms of an appropriate Mukai product, Mukai pairing, I write it here. And once you have these pure spinors, the way you construct the metric is you take the pure spinors and you have these gamma matrices that I briefly mentioned in the last slide, and you can define a generalized complex structure. And from those generalized complex structures, you define the generalized metric. And if you look at the generalized metric, you can read it off like this. So there's the upper right part, this depends on convention, but in the upper right part, you can read off the actual 6-dimensional metric of your spacetime. So this is a 12-dimensional object, that's why the capital indices, but you can read off the 6-dimensional part directly from if you write it on an appropriate basis, defined through here. And now having this, you can read off the B field. Okay, from this generalized metric. You can also read off the Dirac. It's just the determinant of your small g. So basically, these phi plus and phi minus, these pure spinors, encode everything you need to know about your NSNS background. And I'll be talking only about NSNS for now, and I'll very quickly generalize to Ramon. Okay, so as an example, flat space has this metric. This is the generalized metric of flat space, where this G is just the flat metric of complex. I'm using C3, so this is how I would write it. So that's flat space. So all we do, well, what we did, and it seemed to work fine, is let's take the pure spinors of flat space, which, as I showed earlier, I mean, they are just these ones. See, all that's here is wedges between, so these are all differential forms, right? Take them and twist the product. And we twist the product using the linearized star product that I had earlier, that came from the gauge theory side, so it became purely from gauge theory arguments. So it becomes something like this. That's equivalent to doing what is known as a bivector deformation in the generalized geometry literature. We were inspired a lot by this paper of Halmaki and Tomaschello, who did something like that for the orbita. And so basically the claim is, if you want to exhibit this quantum symmetry as a deformation of the non-quantum, basically of C3, because that's the non-quantum symmetry, the geometry is just C3, transfers to our brains, all you have to do is put a star product. Okay. Now, we claim that this is how this CFT symmetry, so what I call the quantum symmetry, maybe I should better call it the Hopf algebra, that's how it's manifested on the gravity side. So basically now, this is a finite, these are forms, so this is a finite product. I mean, you have multiforms, you have to work a bit on this, how to expand them out, but it ends at some point. You can expand them out and you find something like this for the W deformation. We also did it for the beta deformation. Okay, that was kind of easier, but that reproduced Louis Malthussen very easily. Actually, what it reproduces is, and I'll come back to this in a minute, it doesn't reproduce on the nose the CFT background, because all we're doing is we're deforming flat space. So what we're doing is we're deforming flat space, and then we need to go to the horizon limit. Okay, and that background, which is the Louis Malthussen, but before we take the new horizon limit, has been called n equals 2 precursor background. I think Halmaki and Tomaschello used that word. I'm not sure if Louis Malthussen used it. But they have it in their paper, in the appendix. Basically the idea is it's a two-step process. First deform your C3, then add D branes, and then take the new horizon limit. And that will also give you, from a purely NSNS background, you're going to get all the Ramon forms shown up by self-consistency. So you get the geometry right, and then you have to self-consistently solve the equations. That you can do because in these cases also there's no C0 field. So that makes things easier. C0 being the 0.
But you have an H. So from the C3 you have a C3.
Yes, you have the B field strength and the Ramon 3 form field strength. So but that you can self-consistently solve if you have the geometry.
And so you have the background and H, and then you're putting the F3 and the F5 and the F3, but the F5 and the F3 are linear with respect to each other, given the background of H3 and metric. And
so the F5 we make the usual ansatz for the F5, you know, that splits into two spaces because we know what we want. We want.
But it's going to be ISD or not? It's not going to be ISD.
It to be?
The H3 and the F3 together, they're not going to be an ISD pair. They're going to be imaginary Sardur or not?
Yeah, I don't think so. Yeah.
Yeah, no, she shouldn't. So.
I mean, okay. The thing is, there are more normal forms. We have them. I mean, we have them explicitly, but they're too long to write down on a page or whatever. So we haven't actually studied them too much. All we know is that you can plug them into supergravity equations and you get a full exact solution.
But F5 is the usual form. I mean, just
times something in front because which corresponds to the change of volume for the. Basically, you want F5 to be self-dual, definitely. I don't know if that's what you're asking, but F5 is definitely self-dual. So basically, that means because you're deforming the S5, then there needs to be something in front. When the duality
but if you put a probe D3 brane, so the F5 has a coefficient, like a D0 in dx0, 1 to 3, and then plus some transverse direction. So there's a C4 corresponding to that. If you put a probe D3 brane in this background, does it feel a force, or is it going to? The function appears in the F5. So when you have a C, there's a 0, 1 to 3, and then you have some transverse direction. There's a C4.
Yeah.
Is the C4 coefficient the same as the work factor along the space-time? Because in a normal different background, there's a z to the minus 1 times the dx 0, 1 to 3, and now okay, there's a more massive function. But is the massive function the same as the one that appears in the?
Okay, so that's not what we did.
I'm just wondering because I don't have a solution, so I'm just wondering.
My assumption is that you do not feel a force. But we haven't actually looked specifically at the deep brain background. I'll tell you what we did in just this next slide, and then we'll see. Basically, we cheated to get the right answer. So what we did is we deformed these things. We got an n equals 2 background, which is purely an SNS. But this background, it's very easy to see that it's actually a cone. Right? So this is a 6-dimensional deformed background, so it's a C3 deformed. But you can write it as d rho squared plus rho squared times some d omega tilde 5 squared, which so it looks exactly like this. Okay, and so even though it's deformed. So basically, then we just said, okay, let us just follow Mandelstam.
Then it's easy. Then you put the F5, which is beyond that something.
Exactly. So that's exactly what we did. We just said, let's put this is going to go on that side, become an ADS5. Then we get the base of the cone as our internal manifold.
But the cone doesn't have an H field or not? Do you also have an H field on top of that?
Yeah, there is an H field.
There's an H field also. Okay.
Yeah, okay. Definitely there's an H field, but that's what supports the deformation.
Okay.
And the dilaton also is not trivial. I mean, there are things here, but it's purely an SNS. But because of this nice feature, which also Colaxisi had noticed for her deformations in 2006, when you do these kind of deformations, you always get this because you're doing a conformal deformation. So somehow you have to get ADS out, and it works out very simply. It will probably not work that simply for the non-integrable cases. Okay, so that's what we're currently studying. But for this case, I'm actually close to finishing. If you follow this procedure, and then you can use it up to the equations of motion, that you can self-consistently find all the Ramond fields. And this is how the background looks. It's a bit messy. Somebody was asking about how many parameters and all that. So, but it depends on different. I'm not going to expect you to read this, but there are two angles that play a role. We'll call them alpha and theta, and these are angles of the 5-sphere. But now they appear. This is the function that changes our metric. This G. It appears also in the work of Mandelstam, but now it's the special case with the w-deformation. And there are some combinations here. It's a bit messy, so that's the metric. And then you can write down the B field. It looks like this, and you can write down the Ramond fields. Well, we never actually wrote them down, but we could solve them and then put them in the equation so that they work. So we have this background. It's diffeomorphic to Mandelstam because, of course, the double deformation is unitary equivalent, so there had to be a relation. So we could check after the fact that it's actually just a diffeomorphism, but a complicated one from Mandelstam. It depends on 5 angles, so it's a deformed sphere. Okay, we tried to play around a bit with visualizing it. This is not some embedding or anything. This is just plotting the scalar curvature as a function of two of the angles, alpha and theta, so put these to 0, and for some value of w, so w of course expressed in terms of the radius of radius, so here we make it dimensionless, then we get some.
There's no singularity at the point where
no, it's not. It's a smooth. It looks a bit like that, but that's because of the choices of the examples. If you change these phi's, then you can smooth it out. So it's just a way to show that it's not a sphere. I mean, the scalar curvature depends on where you are. Of course, this is not fancy. It's not that we did anything new because it's a background that we could have gotten already. But the new stuff will hopefully this idea, the fact that we did not use TST to get it. At least not obviously, we didn't do anything that involved TDOizing on MD1s. We hope that that will generalize to the non-integrable case, which we're looking at now. So to summarize, we claimed that there's a Hopf algebra structure underlying these theories, and it actually seems to appear at the level of the classical Lagrangian. So if you just classically take the Lagrangian and the potential and you do this deformation, you seem to get this quantum symmetry. It's also a symmetry of the one-loop spin chain, and for a special integral deformation, which is more complicated than just the beta deformation, we found a star product and showed how you can construct the dual supergravity pattern using only that algebraic information. So, of course, we cheated in many ways. Okay, also this, of course, one could have thought more carefully. So, what we're doing now is trying to understand the Quasi-Hopf structure on the gauge theory side, and that's almost complete. And then with Manuela Colazzesi, we're working on more general dual backgrounds. Now, there it seems that this n equals 2 generalized geometry framework that we used is not going to be enough. This precursor that we used doesn't seem to be just an SMS. So we need to use exceptional generalized geometry. And we're working on some aspects of that formalism and understanding how to apply it to our case. So if you do a general deformation, even the imaginary beta, which is not integrable, it doesn't seem that you can write it as an n equals 2 precursor, add some brains and get that. You have to start from n equals 1. So we're also working on similar structures that might appear in other n equals 2 theories with my student Ravi Rabbit. And the hope is that we can also compare it or find some connection to other solution generating techniques that have arisen recently from integrability, but mostly from the sigma model side, string sigma model side. Some of them are classical Baxter equation deformations, Landon deformations. So there must be some relation to those things, but we work from the gauge theory side and purely target space. We never touch the sigma model, so it's kind of interesting to see how they are connected. There's many questions of higher loops that we haven't touched. What happens at non-planar level? Because we used planar structures to claim to understand something about the full non-planar theory. That has to break somewhere, or there must be some issues there. And the final question I want to leave you with is there perhaps some relation between these quantum symmetries, or these Hopf algebras, and the fact that these theories that we're looking at are perturbatively finite? So this is a very uncontroversial statement in 2 dimensions. We know that quantum groups play a huge role in 2-dimensional CFT. Can one find some similar quantum symmetry that plays an equivalent role in 4D CFTs? And perhaps there is some indications that that might work. Okay, thank you very much.
Any questions, comments? Yeah, and of course not perturbatively finite, but perturbatively finite, there's an extra condition, because of course you can have non-perturbative, you can have finite theories, or you can have conformal theories at strong coupling, right? But these theories are order by order finite, so that's what I mean. They're very special in that sense.
So that you need not finite answers.
The beta function is 0 at every order. Well, of course, there's ambiguities, of course, in the beta function, but these are super conformal theories, so you can. That's the argument of Leigh-Strassler. They set the beta function to 0 using the NSVZ beta function, and okay, modulo some discussions of NSVZ and what it actually means. That beta function is 0 to all order.
So, like in the sense that n equal to 4 is fine.
Yeah, same sense as n equals 4. Yeah.
Well, people have found Hopf algebra structure in alternative quantum fields.
Yeah, in Feynman diagrams.
Yeah. So I guess one direction, something in this direction is to express finiteness in that language.
My feeling is that those Hopf algebras are combinatorial Hopf algebras. So it's all about braidings and how, which I think here we're not, of course it's there, but we haven't explored that aspect. But there it's more about the combinatorics of the Feynman diagrams, as far as I understand. Well, here we're trying to do it in the sense of, maybe you're familiar with this concept of quantum planes. Of course, and so basically we're trying to understand deforming the C3 as a quantum plane. I don't directly see the connection between these two things. If you know of a way of seeing that connection, you can let me know. But there seem to be slightly different structures that arise. But of course, maybe they can be combined.
The depth one seems more likely to be connected to perturbative finiteness.
Definitely, I would agree with that.
Because this seems like some property of moduli space.
Yeah, I mean, perturbative finiteness, in my perspective here, just means you deform your C3 to a quantum plane, but you still preserve this. That's what you need for perturbative finiteness. You need your deformation to be able to re-express it as a cone over a deformed sphere base. That allows you to have an ADS5, and that's why it's conformally invariant. So I'm approaching it more from the geometry side, but definitely one should also try to understand what the structures are on the Feynman diagram side. We haven't looked very much, but there has been some work. Valia has worked on this stuff a little bit for the beta deformation.
But then the big picture of guys classifying ADS5 solutions intend to be just by just doing ADS5, forgetting about what the safety dual is just solution. What's the relation between those and these? I mean, people at some point,
yeah. So if you look,
the marginal ADS5 solution, the form with some, transfer.
Okay, so this should exist as part of those classifications. I mean, if you look at work of, some of your colleagues in Paris and so Waldram and all these people, I mean, they definitely write down in many of these, many cases which should include the ones we're looking for. But as far as I can tell, they're not explicit.
Can you just say I have a background which is given by one of these backgrounds, and then I expect, because it's conformal invariant, I expect to be due to some marginal deformation, and then the question is, can you just, for example, put some probes? When you have backgrounds like that, for example, when you have a non-trivial commutator or Feynman in the field theory, you can have, for example, branes polarizing in the bulk. So you can have some linear solution, and then if you just throw in a bunch of brane probes at various orientations, you can see that in this direction there's a potential, and then you just dig off from that. Therefore, in the field theory, I have a phi1, phi3, phi5 term. Because in the 1T5 term, we have put a probe DT brane or some probe D5 brane and some brane. Can you just take those solutions and just reverse engineer them to get what you have here? I'm just wondering from, because they have, again, they have just, they have a huge machinery, they just spit out solutions like crazy. It may be easier to just go backwards.
You might expect that to be possible, but okay, we're not experts on this, and I haven't necessarily tried it. But people have been trying it, and.
In principle, the solutions are there, and probe the fibrane with some diffuse charge on it, which is what you need for this kind of non-commutative. When you have some things taking some non-commutative that's something which you can just plug in mathematics, so you can just take the solution. And
you would think, okay.
Scan over orientations.
Okay, let me tell you what my and I think I see the guy who's picking you up. But maybe if I can take 20 seconds, my perspective on this is that these approaches are missing, at least from my perspective, a crucial ingredient, which is this co-associator story. So when we write our star product, we expect that actually now the new star products we write should involve co-associators to be able to consistently say what you're doing. So when you take your superpotential and you say, okay, now I have a superpotential, what is missing is that people have not put the parentheses. So you have to put the parentheses in a particular placement, and maybe there might be some multiple ways, linear combinations of ways of different parentheses, in order to actually then apply our method and twist and get the correct superpotential. And thus, on the gravity side, also when you're twisting the structures, you have to put the parentheses in a particular order because things are non-associative. So I think that's what perhaps is missing in these constructive methods, that they're not taking into account. Of course, there might be other ways that they are compensating for this.
If somebody has all solutions of some form, so I think those guys, using general geometry, they just give all the solutions which are ADS5, which don't have a C0, for example, but they have everything else.
Yeah.
If you just have that, and then of course, if you find one of their solutions, and let's put some probes, you find that you have some term, Then of course using these algebraic methods, you can just recomplete.
But that's exactly what we're trying to do. We're trying to apply the methods in this exceptional generalized geometry because that's where this belongs to, the general case. Try to apply their methods which are implicit because at some point you need, okay, you can define them, classify them, but then somebody has to come with a specific choice of the pure spinors that corresponds to the precise symmetries that we're looking for. And I think that's the part that we can contribute to this. So those guys have actually, I mean, they have papers where they claim that they've solved this problem, which is true, but it's in an implicit way. You cannot from their papers directly, or I cannot, extract the metric and see, okay, this is a metric, now I can make strings move in it or do something with it.
Oh, I see, the rest of the big part.
So it's, the formalism is there, and it's very powerful, and we're trying to learn it. Just like this was very powerful for n = 2, and it worked really nicely. But you need to also come with a specific.
But I think if you come with your methods on the solution, I think.
So that's what we're hoping to do with Manuela, at least, because who has also long-standing interest in this. I think, are we out of time?
Any more questions? Let's thank our speakers again.
Okay, so if you're checking out today and you have luggage in the other place, there's a van that will take you up there to retrieve the luggage.